Welcome back to Multigrid Methods. Today we are in part two of the second of three slide decks for chapter 7. We're talking about the cell-centered finite difference methods and the multigrid solver algorithms designed for those specific um, types of discretizations. Last time we talked about the prolongation and restriction operators for the one-dimensional cell-centered finite difference case. We went over the fact that the Galerkin condition in the standard setting fails, but we have this thing called the imbalanced Galerkin condition that still holds, and this is going to allow us to carry out our theory. So that was that section. The next section that we are in the middle of is where we're introducing some additional multi-level tools in order to carry out the alpha weak approximation theory analysis that we're going to do to conclude this particular part. So let's go back and do a short review of what additional tools we've just introduced uh, in the last class. So we're still in the one-dimensional setting. And recall that in the one-dimensional setting, we established the fact that our level L stiffness matrix has this form. HL is our mesh spacing on level L. That's always defined, by the way, as 1 over NL. Okay. The interval that we're working on is always omega 0 to 1. NL is just some number. Well, typically we said it's even, and it's given by the formula NL is equal to Q times 2 to the L power for L between 0 and some capital L R, where capital L represents for us the finest grid. So that specifies everything that we need for our one-dimensional finite difference cell-centered problem. As we said before, the stiffness matrix has this peculiar property that it's like the usual standard stiffness matrix, except it's not quite constant on the diagonal. It has this embarrassing 3 in the first and last positions. Otherwise, it's standard. So that's the level L stiffness matrix. Last time we defined what we called the level L discrete minus Laplacian operator. And we said, okay, so suppose I have a piecewise constant function, then I'm going to define this operator on piecewise constant functions as follows. If I want to apply this to a piecewise constant function, I take the coordinates of that piecewise constant function, which are called VL. I'm going to multiply the stiffness matrix times VL to get new coordinates. And then I'm going to use those in a basis expansion to obtain a new piecewise constant function, okay, in VL. And so that resulting function is going to be given by this formulation. We said that we could define an energy bilinear form on VL as follows. So if I have two functions, UL and VL, from this space capital VL, then the definition of this object is going to be an L2 inner product of this thing which we just defined, acting on UL times VL. So those are two piecewise constant functions on the same grid or with respect to the same grid, so that when I multiply them together, I get another piecewise constant function, which is a perfectly good L2 integrable function. I can calculate, actually it's an I just need that it's an L1 function. I can integrate that thing and get a number out in the end. And so that's what I'm going to call the result of my energy form, my energy bilinear form, AL. So I argued that you can prove that this uh, energy bilinear form is symmetric. So it's a symmetric bilinear form. And it is actually bilinear, that is linear in each of the first and second arguments. And furthermore, there's this interesting property that if for these functions from VL, I put in basis functions. So remember, my basis functions are 1 on certain intervals, certain cells, and 0 on every other cell. And they this green function here is an example of one. And if I put two functions like that into my bilinear form, then what I get out in the end is, interestingly, h times, so those indices on those basis functions are I and j. I get HL times the ij coordinate, or the ij entry of my stiffness matrix. And since that stiffness matrix is symmetric, um, I can either look at it as the ith row and jth column entry or the jth row ith column entry. Doesn't matter. So this was an exercise that we're punting to the for later. And now we come to something new called the L2 projection. So what is an L2 projection? I said last time, some of you have probably seen this before, and there are probably just as many of you who may not have seen something like this before. But so let's talk about this first of all. Uh, what is an L2 projection? An L2 projection is something, a formulation, generally speaking, which takes an L2 function and projects it into a subspace. In this case, we're going to go all the way down to a finite dimensional subspace that we're going to call VL. That's the piecewise constant functions with respect to some grid. So we're going to project from L2 functions all the way down to this finite dimensional space. Now, we could, uh, there are lots of ways we can define an L2 projection. And basically by that, there are lots of ways we can pick our finite dimensional subspace of L2. We could even do this, I guess, uh, and I'll have to remind myself if this is true later, project into another infinite dimensional subspace. But here we're projecting into a finite dimensional subspace, VL. So L2 goes into VL. So this operator we're going to call QL, and it's activated for any L that makes sense. So we have these piecewise constant functions for any L between 0 and capital L, where L is our finest level space. And this is our root level or coarsest level space. So the operator is defined as follows, and this is the way an L2 projection is always defined. So for each V in L2, so remember, this is a function which is not even necessarily continuous. It's from this infinite dimensional space called L2, and it could be fairly ugly looking. And we're going to call its projection QLV, and that projection is going to live in this finite dimensional subspace VL. It should be the unique function which satisfies the following prescription. So the prescription is QLV against WL in the L2 inner product should be equal to V against WL in the L2 inner product for any function W L in VL. Okay, so let's make sure that everything in sight makes sense. So we're looking for a finite dimensional object or finite dimensional solution to this problem. So this guy lives in the finite dimensional space, and it's kind of given as the definition of this problem is as a variational uh, characterization or variational description. It's the integral of that against that object, which happens to be in the finite dimensional subspace, and that has to be equal to this. Now, what do we have on this side? this is not a finite dimensional object. This is not in our subspace VL. This is perhaps outside of that space. It could be a very complicated function. But the point is, because both of these functions are in L2, the product is integrable. And so we can integrate this to get a number. Okay, so the first thing and the first question that ought to enter your mind is, does this make sense? Does this give me something which is actually well defined? Okay, I think I answered that question in the next object here. Yeah, basically I'm answering that here, but um, when I give a definition like this, uh, it's not so clear, right? It's not so clear right away that this thing actually gives a well-defined object. So that's the first thing you'd ought to check. Is this thing well defined? And then the second characterization or question in your mind should be, is there an easier way to characterize what this function looks like? Okay. Well, we know that this function has to be piecewise constant because it lives in this space. So the answer, whatever it is, has to be a piecewise constant function. So now I'm going to show you that this thing is well defined, and I'm going to give you a formula for calculating the piecewise constant function every time. All right, so this is like uh, this is saying that that thing that we just defined is well defined. It's well posed. So let L be any number, any grid from or any grid index going from our coarse grid all the way up to our finest index L, and let V be an arbitrary L2 function. Now let's suppose that we can kind of suppose a priori that this thing exists. And if it does, then it has a coordinate vector. All right. So then if I tell you what the coordinate vector is, then I'm telling you everything about this function here. Okay. So suppose we set VL equal to QLV. And if we suppose that thing is in VL, then I can completely characterize that function in VL by telling you what its coordinate vector is. So I didn't say it like this and probably should have, but this is saying that that object that we just gave is well defined. So technically speaking, you should probably say this thing is a well-defined object and its coordinates satisfy blah, blah, blah. Okay, but I'm going to kill two birds with one stone and say, its coordinate vector with respect to this basis BL is precisely given by this formula. And so this tells you exactly how to calculate this object, because if I tell you what are its coordinates in the basis, I'm really telling you what the heights of these individual, remember, VL, if it really is a piecewise constant function, then what I'm doing is I'm telling you the heights of the constant function. I'm telling you its values. Okay, the heights of these little pillars. Okay, so that is precisely what we mean by VLI. That is the ith coordinate of VL. So there's VL1, VL2, VL3, VL4, etc. That's according to our little proposition here, this is 1 over HL times the integral over the ith cell of that function V. So all this is saying is, and it kind of, you might have been able to guess this from the beginning, it's just the average of V. So VLI is just the average of V over the kth cell or the ith cell. So for example, this is KL1, KL2, KL3, and KL4. So the ith cell is generically somewhere in the middle, right? I between 1 and NL. So VLI is the average. So let's prove that from I between 1 and NL that this formula holds. Well, if if um, if VL really is given, uh, it really is QL, and VL is its coordinate vector, then this has to be satisfied. Okay, so its expansion in the basis is obtained via that coordinate vector VLI, I equals 1 to NL. So now all I'm going to do is I'm going to plug that into our formula. So we had this general definition here. So I'm going to plug that expansion into that formula, and that gives me that. Now, of course, L2 inner product is a perfectly nice and bilinear form. So I can pull the summation and these coefficients out. These are the only things that depend on the position, or x. And so this is just a constant. This is a sum. So both of those guys can come out of the L2 inner product. If I do that, then uh, I'm going to get this computation. But let's back up just 1 second. 1 second. Now, I made a little leap here that I didn't explain. I made a small leap here that I didn't explain. How is this defined? This object is defined for every WL in VL. Well, if that's true, then let me explain how I can change this to be something else. Well, if it's true for every WL in VL, and I know that psi Lj is in VL for each j between 1 and NL, then certainly this is true for each of those basis functions. Right? This makes sense. If it's true for all functions, then it's true for every one of the basis functions, kind of trivially. Now, it just so happens that it's not hard to show that if it's true for all basis functions, then using linearity, I can show that it has to be true for any WL whatsoever. So these two are equivalent. If I say it's true for every function in VL, then I can restate this variational equality as it's true for every basis function j between 1 and NL. So that's the small leap I took to get here. Okay, I've simply said, let's let this hold for all of the basis functions. Okay, because that's an equivalent formulation of this variational equality. Now, if you buy that, then if I make this basis expansion, assuming that everything exists, I'm going to put that guy in here. And I'm going to use the fact that if I put in two basis functions into the L2 inner product, then I'm going to get out in the end HL times Kronecker delta, delta ij. So this guy is equal to 1 if I and j are equal, and it's equal to 0 otherwise. Does everyone see why this is true? If I put in two basis functions, maybe they're the same basis functions, and that would be the case that I and j indices are the same, or they're not, meaning that I and j are not equal. Well, if I integrate two basis functions, right? I'm integrating, let's do it this way. I'm integrating two functions that when I make their product, so the first basis function might look like that, right? And then the second basis function, let's make it orange, might be and of course, this is I equals, let's say 1 and I equals 3. If I multiply those two basis functions together, I get 0 because I, um, let's say, let's make j equals 3. So if I multiply these two basis functions together, obviously I get 0 because I and j are not equal. The only way I'm not going to get 0 is if I and j are equal to the same thing. For example, if I and j are both equal to 3, then both basis functions look like this. And if I multiply them together, I get the same thing. I just get one of those basis functions. So I'm integrating over one interval. And of course, the interval is just a cell, and that has size HL. So I hope that that convinces you that that calculation is true, or that fact is a true fact. But in any case, we're going to use that. Um, if I start with this side, let's see, am I doing that? I'm going to flip things around. I'm going to write this over on the left, and I'm going to write this guy on the right. So I'm just flipping that. So there's my definition. I've used linearity to pull the sum and the coefficients out. And now I'm using the fact that psi Li against psi Lj and the L2 inner product is just going to be HL times delta Ij. Well, now using a property of sums and Kronecker deltas, the presence of this delta Ij does is it changes this index I to an index j. And of course, there's an extra factor of HL because of this that pops out as well. So my final result is HLVLJ. And notice what I put in here was the jth basis function. So all I have to do is kind of figure out what is this guy saying. Well, if I multiply v times the jth basis function, that simply becomes the integral over the jth cell. That becomes the integral of v over the jth cell. Why? Because this guy is going to kill off v outside of that interval, outside of that cell. And of course, now I can take HL and move that to this side, and it's pretty clear in the end that VLJ has to be 1 over HL times that integral, the integral over a single cell, and that cell is in particular KLJ. So that's how I calculate the coordinates of this. And this also shows me, sorry, that's how I calculate the coordinates of the representation or the coordinate vector of this guy with respect to that basis. That's how I calculate those coordinates, and therefore that's how I can calculate what this object is. And it just works out to be an average integral over a cell. That proves two things. First of all, it shows that my definition is well defined, makes sense, and it gives you a characterization for that solution. So it takes care of two things all at once. All right, so let's think about doing another operation, which may be a little bit more kind of familiar. So the operation I want to do is I want to take a, a function which is in VL, so this is already piecewise constant, and I want to use the L2 projection to move it as a piecewise constant function to the coarse space, in particular the coarse space whose index is L minus 1. So let's think about what the heck is going on here. So I'm going to start out with a fine level, and let's suppose, just to make things interesting or not non-trivial, let's suppose that VL it has NL equal to 4. So what does this guy look like? So for example, it might be a function that looks like this. It has 4 degrees of freedom. Like that. Okay, so this is our vector or our function VL in capital VL. And what we want to do is take that guy and use the L2 projection to move it to the coarse space VL minus 1. So what the heck is going to go on there? Well, we already know what the answer is because this little result here applies. If I want to calculate the coordinates of this guy in the coarse grid space using the coarse grid basis, then all I have to do is I have to take that function and calculate averages over certain intervals. So now what I'm trying to do is take VL and I want to move it to the coarse grid space. Okay, so what happens when I apply this operator? This operator takes any L2 function and moves it into VL minus 1. QL minus 1 takes any L2 function and pushes it into VL minus 1. That is, so all we're doing here is matching up this index with that index, right? Takes any L2 function. Now I'm just going to realize that VL, capital VL, is an L2, is a subspace of L2. So I can say that QL minus 1, we can restrict its domain if we want to operate that way, right? Because this guy is a VL is a proper subspace of L2. So what I want to do is figure out, well, what does this function look like then in or with respect to the basis from VL minus 1? So here's the answer to this. So let's delete that, clear some room for ourselves. Here's the answer. Suppose that VL is arbitrary in capital VL, and let's set VL minus 1 to be the L2 projection of VL into this space of capital VL minus 1. And let's assume that VL bolded, bold vector, VL minus 1 in RNL minus 1 is the coordinate vector of VL with respect to the basis BL minus 1. So in other words, what I'm doing is I'm translating this function from this piecewise constant space into a vector in R and L minus 1. And let's see, I have a typo here because this one's always a little bit tricky. This minus 1 should be a subscript. So that's a typo. It should be, it's hard to see. So it should be NL minus 1, the subscript being in the minus 1, not NL minus 1, where the minus 1 is not subscripted. Okay, so hopefully I'll see that and make that correction. All right, so that typo aside, then what we can show is um, the the entries of this vector are precisely equal to the entries of the vector with relative to the basis in the fine level space, but where I take two neighboring representations and I average them. Okay, so what this means is, suppose that my, I'm going to make this with, let's use a black for that. So here are the values of that coordinate vector. There's 4 values, right? And it's really just the height of those pillars, right? These guys are little pillars, and the height of those, I can just think about that as being that value right in the dead center. Okay, but I don't have to define it in the dead center. It could be it's just some value in this interval. All right, so that's the representation on the fine grid. That's the vector VL. And now what this result is saying is that the answer to my problem, the representation vector on the coarse grid, is just the average of those two. So somewhere we have to take an average. So I'm going to take the average between that, and that. So that's going to give me this value here. So this purple value in the middle, I hope you can see it, is just the average of this one and that one. And let's do the same thing over here. And the average of these two values is in the middle. So you're going to take the average of, first of all, let's take groupings of two. Okay, I'm going to take the average of those two. Then I'm going to go to the next grouping of two, take the average of those. And if there's more, I'll take the next grouping of two and take the average of those as well. So that's what this result is saying. Now, actually, that makes a lot of sense because it's just going to be given to us by this, and this is given, okay, this value here is an average. So let's just work out the details. So it's really it's just an exercise in notation, although the picture here tells us exactly what's going on. So to prove this algebraically, we just have an exercise in notation. Let's see what's going on. Okay, so suppose that VL is our arbitrary vector in VL. That's the thing we want to push down to the coarse grid. It has a representation in the basis BL using those basis vectors that looks like that. So its coordinates are precisely what we gather into this coordinate vector. So the coordinates and this coordinate vector are related to each other. Now, the next thing I want to say is we're going to have to do this calculation involving the last result. And for that, we need a representation of our cell on the coarse grid. So let's take the ith cell on the coarse grid, KL-1I. It's straightforward to show that that's the union of two cells on the fine grid. Okay, so what's going on here? So here's the coarse grid cell, and here's the next coarse grid cell. You can see that it's just the union of two fine grid cells. They're neighbors to each other. That's exactly what this is saying here. Now, let's use our formula that we had from the previous result. That says that you just take whatever function you're projecting down to into the grid. In this case, we're projecting into the coarse grid space VL minus 1, and we're projecting that function. Well, I have to, if I want to calculate the coordinates of the projection, I have to integrate or average over cells. So I'm going to have to integrate this guy over cells. But now I just said that this cell on the coarse grid is equal to the union of two fine grid cells, so let's write that out. So this average integral writes as two integrals. I keep the same coefficient out front. All I'm doing here is splitting that integral into two integrals. See, the integrand is exactly the same. My limits of integration are the only thing that's changing. Well, now I'm integrating this function, but over only half the cell. Okay, well, or in other words, I'm integrating this over that fine grid cell KL2I minus 1. So that's precisely, if I look at this function here, I'm integrating that function over that cell. That takes care of that guy. And then I'm integrating the same function, but over the neighboring cell right here. And so that takes care of that guy, right? But now the coefficients in front are 1 over HL minus 1, 1 over HL minus 1. When I do this calculation of this integral, I get the value of VL on that particular cell, and the value of VL on this particular cell, times the length of the cell, which in the fine grid is HL. So here are the two values that I get, and the two lengths of the cells that I get. Now, I just realize that HL and HL minus 1 are related to each other. In particular, HL is 1/2 the size of HL minus 1. So here's my HL minus 1, and my interval on HL is half the size. So because of that, I get a cancellation of some terms, and I just get a 1/2 out front. 1/2 times this, 1/2 times that. Okay, so that gives me exactly the formula that I just said. 1/2 VL2I minus 1 plus VL2I. And all that is that average of these two values here. So that tells me exactly what my coordinates are when I do this restriction into the coarse grid. All right. And now let's see. See, I think I had. Oh, okay. So yeah, good. Now I hadn't. So we gave the restriction matrix. We gave the restriction matrix previously. So what was that action that we did just now? This action that we just did was the L2 projection. The L2 projection. But now, if you go back and look, we defined this thing called the prolongation matrix and another object called the restriction matrix. It turns out that this is precisely equal to the action of that restriction matrix. If I multiply the restriction matrix times VL, then all you do is pairwise, you just average these two objects, these two values. So if I really have a cell-centered function which looks like this, remember cell-centered functions are different than piecewise constant functions, but only in the fact that they have values only at the cell centers. So if I apply the restriction operation to that, or restriction matrix to that, then its action is to define another cell-centered function, or a vector, if in other words, and it has half as many entries. In particular, it's going to create those 2 points. So what I've shown here is that this is exactly the same as the restriction operation. So in this case, the L2 projection of a piecewise constant function is the same as the restriction of the corresponding grid function. Okay, so let me say that one more time so it sinks in. The restriction of a piecewise constant function into the coarse space is the same as, gives the same action as the restriction of the corresponding cell-centered function into the coarse grid space. They're the same things, but they're only the same things when I'm really operating between grid functions or in the finite dimensional setting. This object here, the L2 projection, is defined for many more functions than this guy here. This restriction operator, or this restriction matrix, is really only defined for grid functions or vectors. But this object is defined for many, many other types of functions as well. However, when I'm talking about restricting piecewise constant functions or grid functions to the coarse grid, then they become the same object. Okay, now what about the action of the prolongation? So that kind of answers two questions. Uh, what is the action of the restriction matrix, and then what is the action of the L2 projection? We could also ask, what is the action of the prolongation matrix? Well, it actually doesn't make sense for us to talk about the prolongation of a piecewise constant function. We didn't define that operation. However, it does, it still applies in some sense. So here's what I mean. Suppose that I have a coarse grid function, and let's suppose that's a piecewise constant function. Okay, so um, piecewise constant functions and grid functions, we know how to relate the two. So I'm often not going to make the distinction between them. So this is a piecewise constant function on the coarse grid, but suppose it starts out as arbitrary, and suppose that its vector representation in the canonical basis on level L minus 1. I think this may, that's also a typo there. So this guy here needs to be a subscript. Should be NL minus 1. The minus 1 should be in the subscript. That is a typo. Okay, so we're starting with a function on the coarse grid. It's a piecewise constant function, but we know how to convert it into a grid function right away. Now, because of the nesting of spaces, VL, let's start out with actually V0, is a subspace of V1, which is a subspace of V2, which is a subspace, blah, 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 all the way up to VL. So VL minus 1 is a subspace of VL, just the way things are constructed. This guy, therefore, this function, which was arbitrary in VL minus 1, lives also in VL. And now suppose that VL is its coordinate vector, boldface vector, is its coordinate vector with respect to the basis BL. In other words, it's connected to this function via that basis. Okay? And where we're viewing this as a function in VL. Then what we can show is that the prolongation matrix acting on VL is just equal to, sorry, prolongation acting on VL minus 1. So that's the coordinate vector of this guy. If I multiply the prolongation times that coordinate vector, it gives me a new coordinate vector. The question is, well, what is that a coordinate vector of? And it turns out it's precisely the coordinate vector of that same function, but with respect to that different basis. So this, the key to proving this, I'm leaving it as an exercise, but the key to proving this is the same as in the finite element case from chapter 6. It has the same idea. The fact, because we have this nesting of spaces and the prolongation operation is defined in a certain way in the finite element setting. It just so happens that it's defined in exactly the same analogous way here in the piecewise constant setting, or in other words, the cell-centered setting. Now, I need a couple of stabilities involving this thing we're calling the L2 projection. The first stability that I'm going to need, that I'm going to recall later when we're in the heat of this section here on the alpha weak approximation property, is something which we're going to call the H1 stability of the L2 projection. So here's the statement of this. Suppose that QL defines the L2 projection as before, and we're thinking about projecting any function, okay, from L2 into the space VL, where L is between 0 and capital L. Then this operation called the L2 projection is what we call H1 stable in the following sense. There is a constant, I should say here, this is also a typo, because that should say a positive constant. Although there's no other constant that could satisfy this next result other than a positive constant. So there is a positive constant C2 independent of L, very important, such that whenever V is not just in L2, but it's in this more the smoother space called H01. So what is this space? This is the space of L2 functions which have a weak derivative and which is also in L2, and the values of the function at the two boundary points, 0 and 1 in this case, are 0. Okay, so that's this Sobolev space H01. Whenever V is in that space, then this QL operation is stable in the following sense: AL, QLV, QLV. So this is a function in the piecewise constant space, VL, right? So we should remind ourselves this is in VL. This is the same object also in VL. That's the only type of objects that can go into this bilinear form called the energy form, AL. Now this object here, it's pretty easy to show, as long as V is, well, it's actually not exactly true. So this, you can say for sure that this guy is greater than or equal to 0. Okay, it definitely has a sign to it. All right. Um, and actually, we can say as long as V is not the 0 function in L2, then this guy has to be positive. In fact, has to be a positive function. Um, is that true as well? Right. It is true. I was going to say V could be a constant function, but it actually, the only constant function that's allowed in this space is the 0 function. All right, so as long as it's not exactly equal to the 0 function in this space, then this whole thing has to be a positive number. But in any case, this positive number or non-negative number is less than that constant that we just mentioned there, times the integral from 0 to 1 of this object here. What is this thing also called? So this object here is something that we've seen before. Previously, we called this the H1 seminorm, H01 seminorm on 0, 1, right? And actually, the seminorm, uh, we actually don't need this. The seminorm on this space is actually a norm via the Poincare inequality. All right, so this stability is left as an exercise to show that such a thing exists. But what this is saying is it doesn't matter what L is, or kind of, let's see. Yeah, it doesn't really matter how coarse the space is or what the space is into which we're projecting. This number doesn't care about that space, doesn't care what that space looks like. This does depend on L. This cares about exactly what that space looks like. And the stability says that this is always bounded independent of L of this object, which has no L dependence on it at all. And this is what we call a stability. Stability. All right, so we're going to need that. And we're also going to need this thing called the projection error estimate. And this is going to be a lot like a result that we proved in chapter 9. So if you remember that result, I guess some of you are still working on it at the moment, and so it might be familiar to you. It's just that the object wasn't an L2 projection in that setting. It was something a little bit different. Here's the statement of it. Suppose that L is between 0 and capital L inclusive. Then there exists a constant independent of L such that, such that for every V in H1, okay, every V in H1, this one does not have to be equal to H1 0. It doesn't have to be 0 on the boundaries. Then we have the difference between V, this smooth function in H1, and its L2 projection. Remember, this guy is a piecewise constant function in L2 is less than a constant times HL times this is exactly the same object that appeared over here. I guess this object here we should have called that the seminorm squared. And this object here is exactly the same thing, but without the square. Okay, it's got the first derivative, the same as what we have here. L2 norm of the first derivative is the same as the seminorm of V. Now that, in this case, because we're not adding the 0 boundary conditions here, is not a norm on that space, but it still is something which we call seminorm. And so this is what we call an error estimate, because as L becomes larger and larger, or in other words, as HL becomes smaller and smaller, these two functions have to converge, have to become the same thing. Or in other words, the only thing that depends on L is this object here. So as L gets larger and larger, this piecewise constant function is actually converging to this L2 function, or well, it's actually not L2, but an H1 function. What does that look like? What does that look like? It's like this. We have a nice smooth, let's say smooth function, and we have a mesh. So what does the piecewise constant representation of that thing look like? Well, remember what we said before was this is just averages, right? So we take the average on this interval, that might be something like this. And the average on this interval might be something like that. And what about the average here? Something which, this thing, the way I've drawn it, it's coming out too much like a constant function. So let me give it a little bit of interest in curvature here. Okay, so if I hopefully that gives me something a little more interesting. All right. Okay, so what's the average on this interval, this first interval? Maybe something which looks like that. And the average on this one maybe looks like that. Average here. And finally the average here. Right? So that's what this function looks like. If that is V, this thing is V. So what happens as my mesh gets smaller and smaller? Well, these averages should converge, should basically start looking, except for the fact that they're jagged, more or less like this function. So it's going to become like, which converges in L2 sense, according to our result here. Okay, so this is what we call the projection error estimate for the L2 projection. All right, so the next thing we want to talk about is the alpha weak approximation property that we hope to establish for um, our multigrid method applied to this self-centered finite difference type problem. Um, Now, I'm going to call this a cell-centered finite difference type of problem, but I'm going to show just in a moment that actually I'm not going to really think about this, at least from the vantage point of proving this alpha weak approximation property. I'm not going to really think about this as being a finite difference problem in a sense. And I'll show you what I mean in a moment. And it has to do with um, the it has to do with the reason why I introduced these objects called piecewise constant functions in the first place. So you might be puzzled that we introduced these things, but we haven't quite yet used them. It's nice that they're related to cell-centered functions, but who cares? So I'm going to answer the who cares question in this section. We're going to see why we care about these things called piecewise constant functions and why we care about the fact that they're related to these things called cell-centered functions and the cell-centered finite difference process. Well, here's the plan for this section. This is the final, actually not quite. I was going to say the final section where we talk about 1D problems. There is one more section where we're going to talk about 1D problems. The plan here is, well, we are going to we have our smoother in place. We know or have said that we're going to use the alpha Richard or the lambda Richardson smoother. We have our prolongation operator. We have our restriction operator. We know what the stiffness matrix looks like. We know that the Galerkin condition fails. We know that we have this thing called the imbalance Galerkin condition. All the elements of multigrid are defined, and we can do multigrid now using the restriction, prolongation operations, and the smoother that we defined. We can run either a V cycle method, a W cycle. Um, we could do a two grid method. Everything's in place except for the question that we haven't answered do the methods that we want to apply converge? And the final missing piece is the alpha weak approximation property. That's the thing that we could show in this case where we have this imbalanced Galerkin condition. We're going to show that we have this approximation property with the constant alpha equals to a half in our present context. So we're going to do the one-dimensional Poisson problem with constant diffusivity or diffusion. Okay, so that means that uh, so our general problem that we're going to talk about in this chapter is going to be this problem. This D in this context is sometimes called the diffusion constant or the not diffusion constant, but the diffusion coefficient. If we say that this is constant, then we might as well set it to be equal to 1. If D equals 1 everywhere, then we have minus U double prime equals F. So that's what I mean by saying that we're going to solve this for the one-dimensional case with constant diffusion or constant diffusivity. But we can also extend some of our analysis to the non-constant case and also to the case where we have more than one dimension. And we'll talk about that extensively in the rest of the chapter. Now, here's where things might get a little bit strange and weird. And we're gonna reformulate our what once was our finite difference, cell-centered finite difference problem using what's called a variational formulation. So here's the variational formulation. Suppose that f is some given L2 function. Okay, the cell-centered finite difference problem can be reformulated as follows. Now, I might go back in the chapter and reword this because I would say it's not exactly the cell-centered finite difference that can be reformulated. It's a slightly different problem. Here's why. So I'm going to look for a function UL that's piecewise constant that satisfies this equation for every VL test function that's piecewise constant. Now, notice this looks a lot like our finite element formulations, but it's not exactly finite element. Finite element, we defined this guy was the energy interproduct for the regular PDE. So in the finite element context, we were using A, U, and V equals just A prime, V prime, or sorry, U prime, V prime, L2. So that's how we defined this object. Now, that's no longer the case. We're not defining our energy interproduct this way anymore. In fact, we're sticking on a tag here, an extra tag, subscript L. Okay, so, well, this is kind of an analogous object to this object that we use in the finite element setting. It's the energy form that we defined in the last section, slide roughly 3 here. It's that guy there. All right. So it's that weird object, okay, which allows us to define this variational formulation of our quote unquote problem. Now, this F, what does this F look like? I can replace this F here with its L2 projection into the space VL because that's how that thing is defined. If I go back and look at the L2 projection, well, how did I define that? I said QL of F would have been defined as, that's not a vector, equals F VL L2 for all VL in capital VL. All right, so I can either use F, its original self, which is an L2 function, or I can use its representation or its projection into the space VL. That's what we call QLF. I could replace that with that object there. Now, that object is a finite dimensional function, right? And it has a basis representation, and its coordinates in that basis representation are what I can call FL. So that guy can be thought of as a grid function, okay? And the thing that I'm looking for, that's a piecewise constant function. I can also translate that into a grid function. So the question is, could this possibly be related to my cell-centered finite difference approximation? When I imagine replacing the coordinates of f by these objects here. And the answer is it's exactly the same problem. Now, suppose that f is translated that way and has those coordinates. Let's also suppose that ul is that function, the solution to that, and its coordinates are ul in RNL, then we can show precisely that these vectors, FL and UL, satisfy this matrix vector equation. So the proof of that is just a couple of lines long. So let's do that, just so we know that we're all on the same page. Let's add a page in there, move that. Okay. So we said we're going to look for a UL. So we're looking for UL and VL such that ALUL VL equals, and I'm gonna replace that F that was over here with FL, where that just means the projection into the space VL of F for all VL in VL. Okay, so FL here is equal to the projection of F into the space VL. Okay, so let me emphasize that it's in VL. So how can I prove that? How can I prove what I just stated on the previous page? Well, what I'm going to do is I'm going to say, let's let UL be equal to its basis, or its representation in the basis BL. So that's going to be, what do I want to call this? J equals 1 to NL, ULJ, psi LJ. All right, that's good. Now, let's also say, let's let FL be its representation, J equals 1 to NL, FLJ in the basis, corresponding to its vector with its coordinate vectors with those components. And this is the components of my coordinate vector for U. Now, all I'm going to do is I'm going to transform this problem into a equivalent one. This is true if and only if. For this, I can replace, because of linearity, I'm just going to replace the basis functions. I'm going to replace VL with the basis functions. I between 1 and L, right? So now the next thing to do is let's dump these two expansions in here and in here. Now, first of all, this, I forgot to write that, should be L2 and L2 here. Okay, so what happens when we put these basis representations in? So we have AL. Now I can use linearity. I'm going to pull the sum out. J equals 1 to NL U L J. And this is going to become psi Lj psi Li equals. And here we're going to have sum J equals 1 to NL. And F Lj psi Lj psi Li. Now, what did we say was the result of this calculation? We've already done this one. So this calculation here is just going to be HL times delta Ij. So that gives me J equals 1 to NL FLJ HL delta Ij. And all that does is converts this to FLI. What about this guy over here? Let's work on that now. So also we have, let's just flip the sides here. What was the result of this calculation? Well, this calculation gave us, previously we said HL times the ijth entry of the stiffness matrix AL. So that gives us J equals 1 to NL ULJ HL times the IJ or JI entry, doesn't matter because it's a symmetric matrix, times a, let's see, the IJ entry of AL times HL. Okay, now I think we have it all completely right because this is just going to be HL times AL times UL, right? And this object over here is, of course, the ith coordinate of FL. So this proves the result that we wanted after canceling HL. AL, let's see, this should have been the ith entry. So we have ALUL equals FL. So I'm just relating now the coordinates. All right, so that is exactly the same matrix problem that we got when we considered the cell-centered finite difference case. Now, there is one caveat, and that is in the cell-centered finite difference case, the way we calculated the entries of FL was slightly different. So if you remember, in the cell-centered finite difference case, we said if you want to calculate the entries of this vector, then they're precisely equal to applying F at the cell-centered grid points. That's how we defined that. And now here we're saying not so fast. We're defining this guy to be the coordinates of this L2, or this is the L2 projection of a function into this space, piecewise constant space. So these coefficients here and here mean different things in the different contexts, whether you're in this piecewise constant space or in the space or setting of cell-centered finite difference function means slightly different things. However, let's see here. Yeah, just go that way. However, the matrix vector problem is identical. And so that's the important thing. The important thing, well, I should say it like this. The left-hand sides are exactly the same. And that's the most important part for us. It doesn't really matter where the right-hand side comes. On one case or one hand, it comes from the components of a in an expansion of a piecewise constant function, and in another setting, it comes from evaluating some continuous function at cell-centered grid points. All that really matters is, though, the structure of this left-hand side, AL times UL. So this is, we're going to call this without loss of generality, I guess, or without, maybe with a little bit of confusion, we're going to call both of these the cell-centered finite difference problem, even though this guy here is kind of not a cell-centered finite difference problem. It's something entirely its own. It's a different thing. Okay. Now the question is, does this have a solution? Answer, yeah, it has a solution because we just showed it's equivalent to a symmetric positive definite matrix vector problem, right? Or a set of linear equations where the coefficient matrix is symmetric and positive definite. So sure, it has a solution. All right, what's next? The next thing is, how do you compute error estimates for solving this problem here? And what do we what the heck do we mean by error estimates? Well, remember, this problem is a different beast. It says if you're given f, an L2 function, you're going to look for a piecewise constant function which satisfies this variational form, and we're going to call that the finite difference approximation. Okay. So what we mean here is what we have is what we're going to assume is that we have this continuous problem which can be written in this weak form. And so what we're saying is given some L2 function, we can always find a U which satisfies some function from this function class which satisfies this equation, right? That's what we call the weak formulation of the Poisson problem. So on one hand, we've got this continuous solution that satisfies this variational weak formulation, and we've got this guy, UL, which satisfies this quote unquote approximation. So we can ask, well, what's the difference between this guy and that function UL? What's the difference between UL and U? That would be what we could understand as the error. Now, it turns out it's not so natural to formulate things in terms of this error. It's better to formulate things in terms of UL and QLU. In other words, it's better to formulate the error or the question about convergence in this form, UL minus the projection of the true solution into the space VL. That way, both of these operations or both of these functions are in the space VL, and their difference has to be in the space VL as well. Well, what the error estimate that we're going to use says that square root of the energy form AL of that difference, UL minus QLU, against itself, so that's not exactly the error, it's kind of some sort of like pseudo error, is less than a constant times HL to, times the L2 norm of that given function f. Okay, so this says that in the energy norm, we have first order convergence. And this is exactly the same rate of convergence that we got in the finite element case. In the energy norm, we showed that in the finite element case, you have a first order convergence. But again, we said this is different. This is not finite element. This is some weird beast, some sort of different thing. It's weird. That's all I can say about it. It's why are we using this? The answer is why we're using this is we have this nice error estimate. Okay. And we're going to use that or parlay that into this alpha weak approximation property. But to do that, I need a lot more time and explanation to get us there to this last result with this guy here, whose proof is fairly complicated. It involves like 6 slides. So most of what we're going to be involved with on next Tuesday is trying to get through this very long proof. So buckle your seatbelts. That's going to be a bumpy ride. All right. I'm going to stop there and take any questions you guys have.